curious, observant. Look down at a hurricane from orbit, and you are watching billions of dollars of computational effort at work. We spend immense resources trying to predict one specific, highly localized set of physical rules, the weather, climate, and oceans of Earth. But training AI models exclusively on Earthbound data, treating our atmosphere and oceans as isolated problems, creates an inherent fragility. When neural networks learn only from narrow, domain-specific environments, they struggle to generalize the actual physics at play. This chart shows exactly where these models break down. It tracks a typical weather prediction over time. Early on, the forecast maps to reality perfectly, but as we push further into the future, microscopic errors in the AI's math start to compound. Halfway across, the prediction wildly diverges, shattering into a chaotic spray of unusable noise. Physicists call this unstable long-term dynamics. By acting as if Earth's weather is a completely unique puzzle, separate from the rest of the cosmos, we've inadvertently engineered the very wall that stops our models from predicting its long-term future. The irony here is purely mathematical. The Navier-Stokes equations, the strict mathematical rules governing how fluids flow and swirl, do not know they exist on Earth. They operate exactly the same way whether they are pushing ocean water against a coastline or moving interstellar plasma across the void. Look at the swirling vortex of a terrestrial ocean current. Now look at the spiraling arms of a distant galaxy. To a physicist and to the math itself, these are the exact same mechanics playing out at different scales. To master the simulation of our own planet, we have to drop our planetary bias. We need to stop teaching AI how Earth works and start teaching it the mechanics of the entire universe. That is the exact premise behind Walrus, a new foundation model engineered specifically for continuum dynamics, the study of how continuous materials like fluids and gases deform and flow. Instead of just feeding it weather reports, the researchers trained Walrus on 19 wildly different physical scenarios. It learned from astrophysics, acoustics, plasma physics, and rheology, the study of complex flowing matter like mud or lava. Processing this information is entirely different from scraping text for a language model or gathering photos for an image generator. Historical datasets of physical matter are messy, non-uniform, and hostile to standard machine learning. You can see the structural clashes immediately. A high-resolution 2D plane of ocean temperatures trying to communicate with a low-resolution 3D cube of stellar gas, while a third dataset pulses at a totally different time interval. If you dump these mathematically incompatible structures into a standard neural network, the model simply crashes. Making sense of this chaos required a serious engineering intervention. The first solution the team developed is a technique called compute adaptive tokenization. This strips away dimensional formatting, slicing varying resolutions into uniform blocks. But 3D simulations contain vastly more data. To prevent them drowning out smaller inputs, a load-balanced strategy weighs batches, so the AI learns equally from all environments. By standardizing the inputs and balancing the scales, Walrus effectively translates the raw mechanics of physical matter into a unified vocabulary that a transformer model can actually read. Even with the data translated, the team still had to face the monster we met earlier, unstable long-term dynamics. Because AI predicts the future sequentially, a microscopic error becomes a massive hallucination by step 100, fracturing reality into violent, unreadable static. To survive deep into a forecast, Walrus uses harmonic analysis-based stabilization. Think of it as a mathematical shock absorber. It actively filters and smooths out those microscopic errors in the frequency domain before they have the chance to compound. By suppressing that noise, the model holds its grip on physical reality, allowing it to simulate fluid dynamics across much longer timelines than previous architectures. When tested against prior, domain-specific foundation models, the empirical results validate the entire approach. Walrus vastly outperforms them. This radar chart maps the comparative performance. Walrus holds a massive lead in short-term accuracy, while simultaneously stretching far beyond its competitors in both long-term forecast stability and the ability to transfer knowledge to entirely new tasks. By training on everything from solar plasma to sound waves, the model bypassed the simple memorization of Earth's weather patterns and internalized the fundamental behavior of how fluid-like materials act in any environment. The core paradox of the project proved true. Forcing the AI to process the chaotic mechanics of 19 distinct universal environments actually resulted in a more stable, more accurate predictor for our local terrestrial weather. So, what exactly do we have to trade away to achieve this kind of predictive power? We have to surrender our terrestrial ego. We have to accept that our atmosphere and our oceans are not mathematically special, and abandon the idea of pure Earth-only datasets. Large language models mastered the grammar of text. Vision models mapped the geometry of pixels. By standardizing continuum dynamics, we are witnessing AI learn the universal grammar of physical matter. If we truly want to predict the complex, shifting future of our own planet, the most effective strategy is to look up and teach our machines the physics of the stars.